So today we're going to take a look at section 2.4, which is the chain rule. So we have simple derivative rules. That was section 2.2, things like power rule and sum and difference rule and the constant multiplier rule. And then we had two that were not simple, the product rule and the quotient rule. And this one actually has to do with composite functions. So composite functions are functions that are functions embedded inside of other functions. And for that type of a rule, what we have is called, for that type of function, what we have is called the chain rule. So the chain rule, you'll notice, has a g of x sort of embedded inside of a function, f of x, and then you've got the derivative notation on the outside. And what we do is we take the derivative of the outside function, leaving the inside function embedded exactly like it is, not changed at all, and then we multiply that times the derivative of the inside function. Now, some problems that involve the chain rule, just like with products and quotients, are really straightforward, pretty clean to do, and some of them get messy, really, really messy. So let's take a look at a simple one first, right? So one of the ways that you can identify if a chain rule is being used is that there's often, not always, I'll show you examples where that's not true, but there's often parentheses involved. So it looks like you have something where if you isolated the part that's inside the parentheses, that's a function. And if you sort of blacked it out, so bear with me while I do that so you can see what I mean. So if you sort of ignore this piece right here, I highlighted too much. Oh my goodness, that's not what I meant to do. If you sort of blacked this out and you had this just as a power, like just an x inside there, x to the power of 5, that would also be a function. Okay, so it looks like you've got a function inside of something else going on. So when we're working with these, we're starting with the outside function. So the outside is sort of like working your way from the outside in. That's the power 5 on this function. And you guys know how to do the power rule. You've been working with it now for about a week, at least. And so the power rule says, what am I going to do with my 5? Yeah, I'm going to bring it down and multiply it by the 2. So this is my derivative. This would give me a 10. And then I'm going to decrease the power of 5 by 1 and make it a 4. Now, the part that's inside the parentheses, the inside remains unchanged. So whatever it was to begin with, it's still the same thing right now. So for us in this problem, it's 6 minus x squared. So this is the derivative of the outside. It only affects the power 5 business. Everything else remains the same. And then it will be multiplied by the derivative of the inside. So I need to multiply it by the derivative of 6 minus x squared. So what is 6 minus x squared's derivative? Right, negative 2x. And if this were on the gateway, you would stop right there. You would do nothing else. Okay, so this would be my definition of one that's a pretty straightforward chain rule. All right, it has an inside piece that's got a power inside of it. It's got the outside piece, and we do it piece by piece, and we would stop if we were working on the gateway. If we're not working on the gateway, we're working on homework or simplifying for a quiz or something like that, the part that we simplify is we simplify the parts that can be simplified sort of cleanly. So I'm not asking you, in other words, to distribute the power of 4 here. I'm not multiplying this out 4 times, by itself 4 times. That's not necessary. But the negative 2x at the end and the 10 at the beginning, those can be simplified pretty simply, right? Not too bad. So if we multiply those together, I have negative 20x, and then I have my 6 minus x squared to the 4th. And we would stop right there. Any questions on that one? Okay. Now, number 2 is also an example of the chain rule, but it doesn't do what I actually said on the last one that they normally do. That is to say, you don't see any set of parentheses. Now, depending on what the operating system is inside of your calculator, if you were to put this in your calculator might actually require you to use parentheses. So for those of you who have a calculator that you think might require you to use parentheses, where would the parentheses go? Any ideas? Yeah, mine would do it, and it would do exactly what Hayden said. It would force me to put parentheses around the denominator. Like if I put this in my calculator would make me do this, and I'd have this stuff inside here. It doesn't sort of put it into that nice, neat fractional looking form like some of the newer versions do. And the reality is that part that's in the denominator is in a set of parentheses. It's all grouped together. So there's an understood parentheses there, whether there's a visible parentheses or not. And as we're taking a look at this, we actually would like to rewrite this in order to use the rules that we have. Now, could we use the quotient rule? Yes, we could use the quotient rule here, and it would be totally fine if you wanted to. The reason that the quotient rule isn't sort of absolutely necessary here is because the numerator doesn't have any variables in it. It's just a constant. So it feels a little funny to use the quotient rule because when I take the derivative of the numerator, what's the derivative of this numerator? 0. So it's a little awkward. It's not wrong, it's just a little awkward. So I want to show you how to do it with the chain rule, and we would take that denominator, x squared plus 3x minus 1, and we would raise it to the power of negative 1, right? Because everything in the denominator is shifted now. It's in the numerator with the power negative 1 since I moved it up. Okay? So far, so good. Now it's actually in a form where I see parentheses. And it looks an awful lot like the last problem, doesn't it? It really does. I have a parentheses with an exponent, and I'm going to deal with it in exactly the same way I did before. So my exponent's a negative 1. What am I going to do with the negative 1? Bring it down in front. I don't even have to multiply it by anything. And then what will my new exponent be? It'll be negative 2. And like I mentioned before, if you really want to write negative 1 minus 1 on the gateway, you could. It'd be okay. And that would be all right. So the part that's inside, though, in the parentheses, remains unchanged. So it's still x squared plus 3x minus 1. And then I need the derivative of the part that's inside the parentheses. So what's the derivative of x squared plus 3x minus 1? 2x, what's next? Plus 3. Fabulous. Gateway, stop there. So if it's not the gateway, where do I stop? Well, not there. So if it's not the gateway, what do I need to do? Well, right now, when I started this problem, I introduced taking everything that was in the denominator and moving it up with a negative exponent, right? So I'm going to undo that, and I'm going to put it right back down where it was. So in other words, that will become the new denominator. And it will have a power of 2. So it will still have the parentheses in it now because I have a power of 2 on the whole thing. Don't need to square that and multiply it out or anything like that, but I do need to put it back down on the denominator. Now you'll notice there's 2 other pieces that I'm going to have to deal with, the negative 1 here at the beginning and the 2x plus 3 at the end. And both of those pieces stay in the numerator because they don't have negative exponents, right? And so if we consolidate that together, I'm going to have negative 2x minus 3 on top. Just distribute the negative through. Any questions on that one? Yep, Derek.
First step, are we just understanding that we would multiply it by the numerator, which is just 1?
Yes, exactly. And I'll have another example later, but you're right. Yeah, there's an understood 1 out here. Since it's a 1, I didn't write it, but yes. Okay, problem number 3 has 2 distinctly different ways of working the problem. So I'll show you one of them sort of totally fleshed out, and then the other one I'll show you how you would start it, because I don't want to do the problem twice. So take a look at this one. Do you notice that you have 2 rules going on? Isn't that exciting? There is definitely a quotient here, like a legit quotient, not like I have a 1 in the numerator quotient, right? Okay, I have variables on top and variables on bottom. There is a quotient rule going on here that I have to use. But this quotient is also embedded inside of a radical. So I also have a chain rule. So here are the 2 different options of how you could rewrite this and how you could think about this particular problem. So one way to do this is to rewrite all of this, 3t squared minus 2 over 2t plus 3 to the power of 1/2. That's what square root means, right? Power 1/2. So I can do a quotient rule inside of a chain rule. Option number 2 is that we could write the numerator to the power 1/2 and the denominator to the power 1/2. If I think about it from this perspective, the non-simplified version, of course, will look different, but what will happen is that instead of having a quotient inside of a chain rule, I have a chain rule, the top and the bottom, inside of each of my quotient pieces. So the order of what I'm doing gets shifted a little bit, depending on the perspective that I'm working with. I kind of like doing it the first way I wrote it down, so that's how I'm going to show you this particular problem. But either option works just fine. They just look a little bit different in the intermediate steps. So we will do it with this one. Okay? So, just like the last problems, I have a power on the outside. That's my outside function. So the power comes down. I rewrite the inside to my new power. So h prime of t, the power comes down. I rewrite the inside, 3t squared minus 2 over 2t plus 3. And what's the new exponent? Right, negative 1/2. Clean up on this one's not so friendly. Sorry. Now I need the derivative of the inside. Well, that's where the quotient rule comes into play. All right, so quotient rule says what? Where do I start? The denominator or the numerator? The denominator. So the denominator is 2t plus 3. And then what? The derivative of the numerator, which is 6t. All right. Minus the numerator, yeah? Or you want the derivative of the denominator first? Sure, 2. And then the numerator, 3t squared minus 2. I think I got all the pieces. Did we get them all? What's that? One more time, Tanner, I can't quite hear you. It's what? Yeah. 2t plus 3 squared. On the gateway, you get to stop right there. Can I get it? Hallelujah! Right? That's great, but we're not doing the gateway right now, so we're going to see how we're going to clean this thing up, and it isn't very pretty. It just isn't. So, as we start to clean this up, let's actually take a look at a couple of things. So one thing is that I can actually flip this fraction that's to the negative 1/2 and make it to the positive 1/2, right? So if I flip my fraction, I change the exponents from positive to negative. So I could do that here, 2t plus 3 over 3t squared minus 2. And this is to the power 1/2. So let's just kind of clean that piece up for the moment. We'll have more to do with it in a minute, but for now. The other piece, wow, we're going to have to distribute and clean some things up. So let's see, we have 12t squared minus 18t and then we have a negative 2 times 3, so that's negative 6t squared and positive 4. It shouldn't be. Thank you. Positive 18. Okay. And the denominator is 2t plus 3 squared. Okay, so far so good? Great. I have my 1/2. I'm going to rewrite this piece right here with the 1/2 on the numerator and the denominator separately. because eventually I'm going to need it there anyway. So now I have 2t plus 3 to the 1/2 over 3t squared minus 2 to the 1/2. And over here, let's see, we have 12t squared and negative 6t squared, so that's 6t squared. And I have plus 18t minus 4. And then I still have 2t plus 3. Is it plus 4? Thank you. I'm zooming in and out constantly on my iPad. That's why I lose signs, just to let you know. Constantly in and out, so please correct me every time. It'll happen. Squared. All right. Now what? You see anything that we can simplify? There's two different things we can simplify. Okay, so everybody see what Hayden sees. They're the same factor, right? 2t plus 3. I've got a 1/2 factor on top, and I've got a squared factor on bottom. So they can combine. They don't completely reduce one another, but they can combine. How would they combine? Like, what would we do?
Subtract exponents.
Yeah, we would need to subtract exponents. So if I take the 1/2 on top minus the 2 on bottom, what's 1/2 minus 2? Negative 3 over 2. And if I put it on bottom, it'll be positive 3 over 2, right? So I could actually get that piece. We'll fill in some other details later here in a second. But I agree. The 2t plus 3 can have a positive 3/2 in the denominator as its exponent. So that took care of the pieces I've highlighted in red. Manny?
What happened to the negative exponent?
The negative exponent on what? The 3/2?
On the, yeah.
Or on the 1/2 right here?
Yeah.
That one?
How'd that,
We flipped it. Do you see my numerator and denominator switched places? So when I flipped the numerator and the denominator, that eliminated the negative exponent. Yep. And that's actually what's going on the bottom here too, is that I take the 1/2 on top minus the 2 on bottom, which is a negative 3/2, but if I put it on bottom, I have a positive 3/2. Yep. Okay, does anybody see what else I can do to simplify? There's one more thing I can do. Do you see something, Katie? Yeah, exactly. So very good eye. So over here in the numerator, every term right here is even, isn't it? And so I've got a 2 right here in the denominator, and I could actually cancel out and make each of those 1, 2, factored fewer than it was before. I can divide each of them by 2. So that's exactly right. So I can actually rewrite this as 3t squared plus, 18, so 9t and plus 2. So that took care of the 2 orange pieces because I divided each of the numerator pieces that's in orange by 2. And then the other piece that's in the denominator just stays. So I have a 3t squared minus 2 to the 1/2. It would be a good idea to double check that nothing in the numerator cancels. Like, can I factor it rather to cancel it within the denominator? I might stand a chance with something because I do see I've got a power of 3, a coefficient of 3 and a coefficient of 2 at the end. But even if I did, the signs aren't going to work, and the denominator has a 3t squared, not just 3t minus 2, right? So even if the numerator factors, it's not going to reduce with the denominator, so factoring it won't help me, hence it's not necessary. Does that make sense? We're only going to factor if we actually have the ability to cancel something. Otherwise, we're going to leave it like it is. This one's definitely messy. Any questions on this one? I know we've had some of them as we've gone along, but anything else? Okay. So let's try another. Some trig. Same directions. Now, again, you don't see a parenthesis here, but do you know where the parentheses really are? Where are they? They're around the pi x. You're right, Faith. Around the pi x. In fact, I think that all of your calculators put that parenthesis in if you press the word sign, at least all the ones that I see consistently. Hit sign and automatically put a parenthesis right there, right? Yeah. So there is an inside function, it's pi x. There is an outside function, and this time it's not a power. This is the first one we've seen that is not a power as the outside function. The outside function is actually sine. So we start with the outside function, and what's the derivative of sine? Cosine. And the part that's in parentheses remains the same. And then we have to multiply by the part that's in parentheses derivative. In other words, what's the derivative of pi x? It's pi. Yes, it is. Pi is a number. So we have a number times x, so it's pi, right? Not a lot to clean up. The only thing I really can do is move that pi to the beginning. So I've got pi cosine of pi x as my derivative. Breath of fresh air after that last simplification, right? It is. It's a very clean simplification. So some work out cleanly and some don't. Okay, number 5 is a little more complicated. It has a cosine squared in it. Now, we always have that sort of square next to the cosine to remind us that it's the cosine that's being squared. But there is another way to rewrite this that's a little bit more helpful for what we're working with. That is, I can write 5 times the cosine of 3t, all of that squared. Now, you'll notice that I put the parentheses around the 3t when I did that, right? I did. For the same reason that the parentheses were around the pi x over here. Now, the thing about this one that's unique is that there's actually 2 inside functions. Do you see the double sets of parentheses? Yeah. So as I work this problem, I'm not just going to do the derivative of the outside, derivative of inside, and have 2 pieces when I'm done. I'm going to end up with 3 pieces when I'm done because I have 2 inside functions. So, g prime of t. The squaring is the stuff that's on the outside, the farthest outside, right? So I'm going to deal with that first. So what do I do with my square? I bring it down in front. So that's going to give me 2 times my 5 to give me 10. And then I rewrite everything that's inside, which is cosine of 3t. And technically now it has a power of 1. I realize powers of 1 are not very exciting. But I'm just writing it there, kind of like when Derek was asking me about the multiplication by 1, because I want you to realize that if there weren't a 2 there or something bigger, I would still have to put that value minus 1 in that spot. Okay? So I've dealt with the outside part, the squaring part, so now I'm dealing with the first bigger part of the parentheses, that is the cosine part. What's the derivative of cosine of something? Yeah, it's negative sine, and again, of the same inside function, in this case, 3t. Okay, so first I did the derivative of the power of 2, and I'm working my way inward. Now I did the derivative of cosine, and then I'm going to work my way inward one more time, and I need the derivative of 3t. So what is the derivative of 3t? Just 3. Okay, gateway, stop there. There's an insane number of parentheses in this problem right now. And they aren't necessarily all that necessary as we work our way through cleaning this up. One of the sets of parentheses was because I put a power of 1, which is sort of unnecessary, right? The other is because I put the negative beside the sign, and I can move the negative to the front. So there's some pieces of this that clean up really nicely, namely this 3 and this negative and this 10. Those can combine to what? Negative 30. And then I have cosine of 3t. You can put the parentheses around the 3t or not. And I have the sine of 3t. So either like this, or if you want, you can put the parentheses around the 3 t's. Okay, any questions on that one? Double insides. How is number 6 different in the way it's presented? We have some subtraction. So part of it, the 3x at the beginning, is just a simple rule, whereas the other piece is going to be one of our new rules, the chain rule. What else? What's being squared here? The pi x, not the cosine, right? Pi x is being squared. So where the squared is located matters. On the last problem, the cosine was squared. The squaring was right next to cosine. On this one, it's the angle pi x that's being squared. So there's a couple of things that you could do. One is that you could sort of distribute the squaring inside, so you could write it as pi squared x squared. Feels a little funny to write pi squared, but you could do that. But either way, you still have a function inside of a function. So I'm going to leave it like it is, just to show you what happens, because then I have another inside function going on, and we can take a look at it from that perspective. Whoops. All right, so y prime, 3x. What's the derivative of 3x? 3, right? We like that one. That one's very friendly. And the outside function here is actually the cosine part. So all of this is actually what's going on. So if we're working our way inward, the cosine part's what I want to deal with first. Or maybe it would be better if I write it like this as a reminder. Let me do that one. So the cosine is on the outside, and then the squaring part is on the inside. So what is the derivative of cosine? Negative sign. And there's already a negative here, right? So I'm going to just change my negative as I go. So this is now positive 5 sine. Okay, the 5 stays because it's a constant multiplier. Cosine becomes negative sine, so it cancels the negative that's already there. And the inside function remains the same, so it's pi x squared. Now I'm ready for the pi x squared part. Okay, I've got a squared. So what do I do with the squared? Bring it down to a 2. I rewrite my pi x, right? It's the part in parentheses, and decrease my power of 2 by 1. So I have a power of 1. And then I would have the derivative of pi x. We saw that one in a couple problems ago. What's the derivative of pi x? Pi. Again, it's not the only way to do this problem. I could simplify it a little differently at the beginning instead. I'll end up with the same answer at the end, but the intermediate steps might look a little different. So this would be one version of this. Now because this is because this is to the power of 1 right here, I don't really need it there, right, in terms of simplifying. I can combine all of this at the end with the 5 right here at the beginning of sine. So my 3 stays. I have 5, and then I have pi squared and x. Oh, 10. I forgot my 2. You're right. 10 pi squared and x. And then I have the sine of pi x squared. Do you notice the very beginning of each one of my problems it says y prime equals g prime of t equals y prime equals h prime of t equals g prime of x? You see all that, right? We have this tendency in math we just like to put equals on something. Do you do that? Lots of people do. Make sure you define what you're having it equal. It doesn't equal what it started at, right? This is not the same as g of x. It's the derivative. It's g prime. So somewhere before you start putting equals and all the things, define that this is derivative that you're actually finding. All right? So somewhere at the beginning of all your equaling, make sure you've rewritten y prime or g prime of x or whatever. You could leave it off. I put mine at the very end, so you'll notice I have this thing, right? See all my equals? but I wrote it at the beginning here. So, and then I usually write it at the end because I box my answers in as a final step. Okay, let's take a look at a different variety of a problem. This one wants us to evaluate the derivative at a given point. So we're still finding the derivative, just like we were in all the previous problems, but at the end, we're going to put in the x and the y if we needed to. We won't need to for y, but we will later on. So we're going to plug in x at the end. So, for starters, just like what we were doing in the previous problems, we're going to rewrite this in a notation that's helpful for our our chain rule. Okay, denominator written to the power of -1. Okay, is that good so far? I mean, you could just leave that as equals, but this is f of x. I've not taken any derivatives yet. I'm still right now just rewriting. All right, but I am ready to take a derivative. So, what's my first step? Pull the -1 down your right lane, so I'll have a -5. What am I going to write next? Yes, the inside unchanged, x to the third minus 2. And what will my new exponent be? -2. Okay, am I done? Nope. What am I missing? Tanner, can you tell me what's next? Right, the derivative of the inside, which would be what? 3x squared. Okay, now technically, you don't even have to simplify this version of it if you don't want to. You just need to evaluate it at x equals -2. Okay? Now, it might be simpler to clean it up a little bit before you plug numbers in. Just depends on the problem you're working with. So I would probably clean this one up a little bit just because I think it's kind of messy the way it looks right now to me. So I would multiply these two pieces together, which gives me a -15x squared. And then my denominator is x cubed minus 2 squared. So that would be a cleaned up version of the derivative. This is f prime of x, but I want to find f prime of -2. So I'm evaluating. So -15 times -2 squared over -2 quantity cubed minus another 2 and then squared. Lots of squaring going on. So simplifying the numerator will just work from the inside out. What's -2 squared? 4, and 4 times -15? -60. And you don't necessarily have to show a lot of cleanup steps. Your calculator can do most of that for if you wish. What's -2 cubed? -8 minus 2? -10, and -10 squared? 100. And if we reduce this fractionally, I have -3/5. Or this one reduces really nicely to a decimal if you wish it. It's -0.6. Either way is perfectly fine. If the fractional does not reduce to a terminating decimal, you need to leave it in fractional form. For example, you can't write down 0.6 repeating. That's not really good mathematical notation. So we avoid that for most parts of calculus, okay? We leave it as 2/3, excuse me. Okay, so any questions on that? It's the same stuff. We're just evaluating at -2 at the end. All right, one more variety that you'll see happen in this section, and these are happening in all of our sections, so it should come as no surprise, is that on this one, we're actually going to find an equation to the tangent line, and then we're going to verify it with the graphing utility. Oh, I didn't use the graphing utility. Let me actually talk about what that would be. If you wanted to use the graphing utility to verify this, do you remember how we did it? It's been, a few days. We used inderiv. Do you guys remember that? So you put your equation into y1. So in y1, you put your equation. And then you do inderiv is underneath math 8. Okay, so if you go underneath math 8, it'll give you one version or the other of inderiv. and you can evaluate it at a specific point, -2 now, and it will tell you -0.6 or -3/5. Okay, if you weren't here when I discussed those and you're not sure what I'm talking about, please come see me or ask a neighbor, see the Success Center, that good stuff, because it is a very helpful thing to be able to verify. All right, so on this one, we're going to actually create the equation of a tangent line. So as always, the equation of a line, one version of it anyway, is y = mx plus b. We need m, and m is a slope of a tangent line, right? So we need the derivative. So anytime we're looking to find the slope, we're looking to find the derivative. So this is not a terrible one. If you wanted to square it and multiply it out and use simple rules, you could do that. We're in the chain rule section, so we'll use chain rules. But there's a couple of ways you could do this problem. If you use a chain rule, what is my first step? Bring the 2 down. What would I do next? Yep, stuff in parentheses stays the same. The power's 1, which is friendly. And then I need the derivative of the inside. So what's the derivative of 4x cubed plus 2? Close. I think you said 4. Did you say 12? And I just heard wrong? Somebody said a 4. Yeah. So 4 times 3 would be my 12. So I'd have 12x squared. Okay. So we're not really all that interested in cleaning this up. We're really interested in evaluating this. So if you wanted to, you could evaluate at this point. We could actually find y prime of 1 without cleaning anything up. This would be 2. I'm sorry, not 1, -1. It says -1 here. So I would have 4 times -1 cubed plus 2. And then I would have 12 times -1 squared. If you want to clean it up before you do that, that's fine too. It doesn't matter. So inside right now, -1 cubed is -1 times 4. Did I miss something?
4x cubed plus 30.
Oh, yeah. Thank you. It's that zooming in and out business. Promise. Thanks. All right, so we have -4 at this point. Plus my 3 gives me -4 plus 3 is -1, right? And then this is just 12 at the end, agreed? So what's my slope? Yep, -24. And then if you're trying to find your b, right, your y-intercept, you can use y = mx plus b. I have -24 for m. I have the point xy given to me. X is -1. Y is +1. So now I have 1 = 24 plus b. So what's b? Yeah, -23. So my tangent line is actually y = -24x minus 23. And when I'm asked to find the graphing utility verification, it means I need to graph it. So let's go through that one on this one, especially when it gives it to you something like this, is they're probably going to have you actually graph it inside of WebAssign. So go ahead and grab your calculator. You're going to graph the original equation. So this one right here would go into y1, and your tangent line goes into y2. And the way that you would do this if you were working on a quiz for me or a test or something like that is that you're actually going to just sketch the graph. A sketch, of course, is fine. So we want the original graph, 4x cubed plus 3, quantity squared, and the derivative, -24x minus 23. And it should look something like this. So that's one of them. And that's the other one. Do your graphs look kind of like that?
Just a
My scale's probably not real great, but what's that, Hayden?
It's just a lot smaller.
It's a lot smaller. I'm zoomed in on mine probably when I drew my graph. Does it seem reasonable? Does the tangent line look like it seems like it's tangent line? It's plausible. The graph seems plausible, and that's kind of what we're going for when we're verifying with the graphing utility. Nothing about it verifies it 100%, but it's supposed to be verifying it sort of reasonable. Is this reasonable? Okay, any questions on that? All right, so on Thursday, you'll have finished 2.4 when you come to class on WebAssign. Let me show you something else real quick, and then we'll be done for today.